Log on, tune in, find out. Another good idea from Cambridge.
The first of, I hope, a series of ITGP lectures, special lectures. So maybe that needs a little bit of introduction. So ITGP is an ESF network. It stands for Interactions of Topology and Geometry with Mathematical Physics. It is a European network funded by the European Science Foundation, and there is opportunities there for support for workshops, summer schools, conferences, and there's also possibilities for exchange grants, support for that, and for short visits and so on. We try to support various activities lying inside our interest area, and also we will now try to somehow arrange activities ourselves. And the sort of thing that we are taking initiative here is the sort of the first one here, namely these two lectures this afternoon. And we'll try to see if we cannot somehow continue this at various locations around Europe where we will have ITGP activities. So maybe I can just write on the board our web address. So it's very easy, and all you have to remember really is our acronym ITGP, or just remember it's a network, so it's .net. But anyway, I think we should get on with the scientific part of this afternoon. So we could think of absolutely no better to give the first lecture in this series, but Nigel Hitchen from Oxford. And indeed, we just talked about it. This man needs absolutely no introduction. So please, Nigel.
Okay, thank you. Okay, thank you very much. So, some of you may have heard me give a lecture here about 2 weeks ago about Poisson geometry, and so it might come as no surprise that this talk is also about Poisson geometry. But it's about the type of holomorphic vector bundle that goes hand in hand with an underlying complex Poisson manifold. And although I may say that Poisson geometry, of course, aligns itself very well with some of the aims of ITGP, in particular deformation quantization, that's not the direction in which I want to talk. And more, I want to show how some of the problems that arise, or the issues that arise in studying Poisson modules, actually relate quite closely to some of the themes of the current program here at the Newton Institute. So let me begin just by reminding you what a Poisson manifold is. And so usually a C-infinity Poisson manifold is a manifold where the ring of C-infinity functions is given this bracket operation which satisfies these conditions. Now I'm going to be looking at complex manifolds, compact complex manifolds. So we can't use the global definition, but you could say that it's a holomorphic bracket on the ring of the local ring of holomorphic functions. But there's a better way of saying that in more tensorial terms. So a complex Poisson manifold is a complex manifold which has a Poisson tensor. So this is a section of the second exterior power of the tangent bundle, which satisfies an integrability condition, which is one way of saying it is that we take this bracket, this Schouten-Neuenhaus bracket, and it must vanish as a section of the third exterior power. And using the bracket, you can define this, using the Poisson tensor, you can define this Poisson bracket. So here briefly, so the Poisson bracket is given by differentiating the two functions and then contracting with the tensor. And this integrability condition is equivalent to saying that you take the two vector fields. So the Poisson tensor gives you a map from the cotangent bundle to the tangent bundle. And so if I take a function, I can take its derivative and then apply sigma and get a Hamiltonian vector field. Then another way of saying this integrability condition is to say that the the two Hamiltonian vector fields of f and g, the commutator of them is the Hamiltonian vector field of the Poisson bracket. So that's, but essentially what we're looking at is a complex manifold with a Poisson bracket with a Poisson tensor which satisfies this integrability condition. Now the easiest place to look for these is in two dimensions because, why? Because there are no free forms, there are no the third exterior pair of the tangent bundle, which is just two dimension, is zero. So there's no integrability condition. So what we have is that we have a holomorphic section of a line bundle here, the second exterior pair of the tangent bundle. So this is the anti-canonical bundle. So basically a Poisson surface is just a surface with a non-trivial anti-canonical divisor. And from the adjunction formula in algebraic geometry, generically, if it vanishes in a non-degenerate fashion, then it vanishes on an elliptic curve, but there are, of course, various degenerations which are possible. And if you want a classification of these, it could have been done years ago, but it was, in fact, only done quite recently. Essentially, the Poisson surfaces are rational or ruled, but you have to blow up. Of course, you need an anti-canonical divisor. So if you're blowing up points on the projective line, you have to blow them up rather carefully. So, and the simplest case, of course, is the projective plane, where the anti-canonical bundle is of degree 3. So an anti-canonical divisor is just given by the vanishing of a cubic polynomial, and so, but if you like, if you want to think of the standard one, if you want to think of removing the line at infinity from the projective plane, what you've got left is C2, and this is the standard Poisson structure, constant Poisson structure on C2, that extends to a Poisson structure on P2, which corresponds to the cubic curve, which is a line, the line at infinity with multiplicity 3. So that's the most degenerate Poisson structure on P2. A generic one is given by a cubic curve, a non-singular cubic curve. So those are, okay, so now what is the general picture? And I'll talk later about higher dimensional examples. So the general picture is that we have this this bivector, this holomorphic section of the second exterior power, and you can ask, well, what about its rank? So, for example, if its rank as a bilinear form, if its rank is if it's everywhere non-degenerate, then that's equivalent to having a holomorphic symplectic manifold. But typically, this Poisson tensor drops rank on certain subvarieties. There's basically a stratification of a Poisson variety, a Poisson manifold, by the rank of sigma. And this degeneration is in some sense very well aligned with the Poisson structure, because each of these subvarieties, the smooth part of it, is itself a Poisson manifold. So you get an induced Poisson structure on these subvarieties. So this is a particular case of a submanifold or a subvariety which is given by a Poisson ideal. So you can talk about Poisson ideals, which are ideals in the ring of functions, but which are ideals also in a Poisson sense under the action of the Poisson bracket. So this is an important fact that, when we look at a Poisson variety, a Poisson manifold in general, what we hope to see is this stratification by various lower dimensional Poisson varieties. And the place to really learn about this is this paper by Poisson, where there are a lot of key ideas in holomorphic Poisson geometry, and many of these ideas these definitions are actually phrased there for the first time. So, as to this stratification, I've only given you some examples of surfaces. So, it's just so generically on a surface where the section of the anticanonical divisor is non-vanishing, then the rank is of this Poisson tensor is 2, so that's the generic situation. But then it just drops. Of course, it has to drop by 2. It's a skew symmetric form, so it drops by 2. So it drops down to 0, of course, on the elliptic curve. So the stratification is a rather simple one for a surface. But what it means is that in the complement of that elliptic curve, what you have is a holomorphic symplectic structure, and sometimes it's useful to think of it that way. Okay, so what are Poisson modules? So these are as I say, it's a type of holomorphic vector bundle which is particularly adapted to a holomorphic Poisson structure. So there are different ways of describing it, but essentially it's given by a first order holomorphic differential operator going from the so it's locally defined because there may not be any global sections of V, so it's defined on local sections of V, taking values in the tensor product of the vector bundle V and the tangent bundle. So a connection, of course, is a similar sort of thing, which takes values in V tensor T star. So you could think of this as, instead of being a covariant derivative, as a contravariant derivative. On the other hand, so first order linear differential operator has a principal symbol, which is a homomorphism from V tensor T star into whatever the target vector bundle is. And in this case, it's the symbol is basically the Poisson tensor, or if you like, one tensor with the Poisson tensor. So a connection is basically a first order operator whose symbol is the identity. And what it means is that we can, why is it called a Poisson module? Because using this differential operator, we can define an action of functions on sections, on local sections of the vector bundle V. So we take the derivative, if you like, using the differential operator, and then we contract or we evaluate, not in a tangent direction, but in a cotangent direction, the direction given by df. Okay, so ds takes values in V tensor T, and then we evaluate the derivative of f on the tangent vector part. And then what we require is that this action should be a Poisson action. In other words, that the commutator of these two should be the action of the Poisson bracket. And that is a secondary condition. It's if you like, a zero curvature type of condition on this operator here. So, for example, if the Poisson tensor were non-degenerate everywhere, then that symbol sigma would be invertible, and then this operator will be exactly the same as a holomorphic connection, and this condition will be that that connection is flat. So it's quite a strong condition. It's if you like, it's a Poisson version of flat connections, or you could extend this to D modules if you wanted to. But the problem then is the challenge is to actually find holomorphic vector bundles which admit such a structure. And one of the features that this has, important features, is that actually if you restrict to a Poisson subvariety, so that means again a subvariety which is given by locally by the vanishing of functions which form a Poisson ideal, then you can restrict. So if I have a Poisson module and I restrict it to a Poisson subvariety, then it becomes a Poisson module with respect to the Poisson structure on the subvariety. So in particular, when I have this stratification by the subvarieties on which the rank of the Poisson tensor drops, then on each of those a Poisson module becomes a Poisson module on the smaller variety. Okay, so let's just discuss this, the obstruction. First of all, the obstruction to finding a first order holomorphic differential operator. because that's the first obstruction. Then, of course, there's a second obstruction, which is to have this zero curvature condition. So the Atiyah class is the sort of Czech version of, it's the class which generates the Czech versions of the Chern classes, but it's essentially the obstruction to the existence of a holomorphic connection on V. So there are various ways of describing this class. One of them is if you take the bundle of holomorphic 1 jets of V, that's an extension of V by V tends to T star. That extension class is this. It's the obstruction to splitting. The splitting of this jet sequence is a connection. So, we don't want a connection. What we want is an operator going to V tends to T, and the obstruction to getting that is applying sigma to this Atiyah class. So in order to find the D, there's a process which is this. You look at the Atiyah class of, given your vector bundle V, you look at its Atiyah class, and you apply sigma, and then you want that class to be equal to 0. And there's one line bundle, or one family of line bundles, which is always a Poisson module, and this is the canonical bundle, or some power of the canonical bundle. So in fact, what this says is that actually if you take the first Chern class of the tangent bundle, so that's the same as the first Chern class of the anti-canonical bundle, then if we apply any holomorphic Poisson tensor to that, then we get 0 in this space here. Those of you who were at my lecture a couple of weeks ago might think that I was basically interested in the classes where applying sigma gives me something non-zero here, because they give me infinitesimal deformations of the Poisson manifold, which, as I showed, were actually integrable. Anyway, so the canonical bundle is always an example of a Poisson module. Just to see why that's so, let me just say that how do you make it so? Well, here I've done it for a power of the canonical bundle. So if I take a local holomorphic function f, I can take its Hamiltonian vector field x, and then there's an obvious action of x on sections of powers of the canonical bundle. It's the Lie derivative. If you write down the Lie derivative in local terms, then its action is like the divergence, if you like, of the vector field. But now, if you spell this out, so the vector field is now a Hamiltonian vector field, so it's written in terms of the derivative of the function and the Poisson tensor like that. But when we do this differentiation, then the second order term, the second derivative here in f is symmetric, but sigma is skew symmetric, so that term disappears, and what's left is something which is linear in it's first order in the derivative of f. And so, if you like, this is the whole point, that this Lie derivative action actually it involves just the derivative of f, and for that very reason we can, if you like, extend it to any one form, which it defines the derivative. You see, this wouldn't happen if I took the tangent bundle, let's say. You might say, well, take a function f, take its Hamiltonian vector field, take the Lie derivative of a tangent vector, then the expression we get would involve second derivatives of f, and that does not give you a Poisson module. So the canonical bundle and all powers of the canonical bundle, these are Poisson modules. But in general, it's more difficult to find other examples. So here are some of the questions, so first of all, how do you construct them? After all, it may be difficult in any given case to find any at all. The other is, how do they depend on the Poisson structure? If I take a different Poisson structure, do I get a very different family of Poisson modules? And the last one is, can you define moduli spaces? So this last one, I think, is particularly open because we usually need some stability condition to define a moduli space, and it's not at all obvious what stability condition could incorporate the Poisson structure as well as the holomorphic structure. So what I'm going to do is to give you, if you like, some examples of the simple examples of Poisson structures, well, of Poisson modules in 2 dimensions. And then I'm going to talk about Poisson structures in higher dimensions because it's far less easy to find them. And then finally I'm going to talk about Poisson modules in 1 dimension, which you might say is trivial, but it's not as trivial as you might think. So let's start in 2 dimensions. So again, we're just considering a Poisson surface, a surface with an anticanonical divisor, and let's look at rank 1 Poisson modules. So line bundles. Which line bundles are Poisson modules? Well, the canonical bundle, I've just told you, the canonical bundle and or its powers are examples, but are there more? Well, I want to show you how, okay, there's a general remark here. So suppose I take the anticanonical bundle, then sigma, the Poisson tensor, is a section of that line bundle, holomorphic section, and of course the Lie derivative of the Poisson tensor by any Hamiltonian vector field is of course 0. It's preserved by a Hamiltonian vector field. So what that means is that if I take the Poisson module structure, the canonical Poisson module structure, this differential operator D, then actually the sigma, the section given by the Poisson structure, is satisfies this equation. It's kind of constant with regard to this contravariant derivative. But it's not, that's true about the whole section, but it's equally true of any component of the anticanonical divisor. So in the generic case, I've said the anticanonical divisor you expect to be an elliptic curve, smooth elliptic curve, but it can degenerate. And when it does degenerate, then each irreducible component is also invariant under this, this Hamiltonian vector field, and it's not hard to see that actually the divisor defines you a line bundle, which is again a Poisson module. So here's an opportunity to kind of compare 2 extremes in 2 dimensions. So what I'm going to do is to take one extreme which has a lot of Poisson modules and another extreme which has basically only one. And these are both given by blowing up points in P2, rational surfaces, but in this first example I'm going to keep on blowing up one point over and over again, and in the next case I'm going to blow up some generic points, at least generic points on an elliptic curve. So here what we can do, okay, I'm doing it very explicitly here, but you take a non-singular cubic in P2 and you look for a point of inflection, and then you take the tangent line to see at that point of inflection, and then you take the cubic which is the triple line there. So you have 2 cubics, so you have a pencil of cubics, which in fact you can put in this Weierstrass form if you like. So it's like, so T is varying and C is fixed. So here we have this, this pencil of cubics. And what you can do then is that you can keep blowing up this inflection point in such a way that you get an elliptic surface, a rational elliptic surface. So it's a family of elliptic curves fibered over the projective line, and the point at infinity is a highly singular rational curve, highly singular elliptic curve. It's a union of rational curves, which in Kodairo's classification I think is called type 2 star, but it's an extended E8 configuration. So it's got, in fact, it's got 9 components. So here's the sort of diagram. So each one of these is a rational curve, and they intersect according to this diagram here. So what did I say before? I said that every irreducible, so this is an anticanonical divisor. So what I said before was that every component, irreducible component of an anticanonical divisor, defines me a Poisson module. So here we've got 9 of them. On the other hand, we have an elliptic surface, so C1 squared is equal to 0. So C2 is 12, which means that the middle cohomology is just 10-dimensional. And so if you like, all but one. So basically what we can say is that the Poisson modules, their Chern classes, are given by the orthogonal complement of the first Chern class. So C1 squared is 0, so C1 is included in its orthogonal complement with respect to the intersection form. So here we have a surface, Poisson surface, with a lot of rank 1 Poisson modules. On the other hand, if we look at the second example, if you take a non-singular cubic curve in P2 and you blow up at more than 9 points on this cubic, then you get C1 squared is negative, and we get it. This is still a Poisson surface because there's this elliptic curve left to be an anticanonical divisor on the blow-up, and so we still get a Poisson structure upstairs. But now we can ask how many Poisson modules are there for this one, and so you can look at. Okay, so now this is just in 2 dimensions. So actually, this Poisson map going from T star to T is just tensoring with a section of a line bundle. So we have this exact sequence of sheaves, and if you look at the long exact cohomology sequence, then this is what we're looking for. Okay, we're interested in the kernel of this, at least the integral classes in the kernel of this. And on the other hand, if you blow up these 9 points, there are no global holomorphic vector fields. So this is the picture that the kernel of this sigma map is the sections of the tangent bundle of the surface restricted to the elliptic curve. But this is an extension by the normal bundle. This has negative degree on the elliptic curve, so there's just a one-dimensional space of sections. Whoops. And so there's just a one-dimensional kernel to this map sigma. And of course we know that there's always something in that kernel, namely powers of the canonical bundle. So in this case, the only Poisson modules are powers of the canonical bundle. So here, in these 2 examples, you can see that this question of describing the Poisson modules, even for rank 1, depends crucially on the Poisson structure itself. The generic one, you don't get many. For the generic one, you only get the obvious ones, but for rather special Poisson structures, you get several. So that was just the rank 1 situation. So now you can try and look at rank 2 holomorphic bundles, rank 2 holomorphic bundles on Poisson surfaces, and see whether they have any Poisson module structures. And there's one very old construction of surfaces, the Serre construction. No, sorry, it's a construction of rank 2 bundles on surfaces. So this says that if you give yourself k points on the surface and some scale factors, lambda I, which sum to 0, then you can find, well, this is the particular case that I'm interested in, you can find a rank 2 vector bundle V whose determinant bundle is the anticanonical bundle, and a section which vanishes at these points, and for which there's an invariant involving the derivative at these points, which is the given scalars. So this means that given any surface and set of points on it, and these numbers, then you can construct some vector bundles, holomorphic vector bundles. And you're constructing them in such a way that there is a section, so there's a map from a trivial bundle to this rank 2 bundle, where the quotient is the ideal sheaf of this set of points tensored with k star. So that's the standard construction. Now you can use that to construct to construct Poisson modules if you choose those points carefully. So here's the exact sequence of that, long exact sequence of that exact sequence of sheaves. And let's suppose that, so for this rational surfaces, then this certainly vanishes. So there's a question here of looking at trying to find other sections of the vector bundle V. And of course, if you have a section of the anti-canonical bundle which vanishes on these points, then you can find a second section of V. So, and it's a second section T such that this S wedge T vanishes. Well, it's given, this is a section of the anti-canonical bundle, so it's a section which contains these points. So turning it all around, if we take a Poisson structure, Poisson tensor sigma, a section of the anti-canonical bundle, and if we take a set of points on that elliptic curve and we apply the Serre construction, then what we get is a rank 2 vector bundle with two holomorphic sections which become linearly dependent on this elliptic curve. So you can use that to define a Poisson module, because what does it mean? It means outside of the elliptic curve, these two sections S and T are linearly independent. And so you can define a flat connection on that bundle outside the curve by saying that these are going to be covariant constant sections. So remember, that's really what we need for a Poisson module, that where the Poisson structure is symplectic, then what we have is a flat connection. Now, and then the question is, what happens as you approach the elliptic curve, the vanishing locus of the Poisson tensor, and then you can actually find just by a local calculation that actually this extends. It doesn't extend as a flat connection, but it does extend as a Poisson module. So this classic construction of vector bundles, when you take the points to generate the vector bundle to lie on the zero set of the Poisson tensor, then this does produce you Poisson modules. And that it does this for whatever Poisson structure you've got. So when we go to rank 2, then in fact you do have means of constructing several of these, but what the moduli space is in general, well, I have no idea. So now let me talk about higher dimensions. Now, higher dimensions is more tricky because the Poisson tensor satisfies an integrability condition. And in fact, when we talk about higher dimensional Poisson manifolds, it's all very well to talk about the properties that they have, this stratification by the rank of the Poisson tensor, but it's a little bit like Mrs. Beeton's cookery book, the famous recipe for rabbit stew. It says, "First catch your rabbit." And so in this case, first of all, you've got to find some Poisson manifolds, and it's in higher dimensions. It's not at all easy to do that in this holomorphic context. So what I'm going to do for the next 10 minutes is to tell you really not so much about Poisson modules, but where you might look for them and what sort of Poisson manifolds you can get in higher dimensions. And in particular, since I was talking about projective plane, what about Pn itself? Is Pn for n bigger than 2, can it be a Poisson manifold? The answer is it can, and it can because of basically, well, there are different ways of seeing this, but the one I want to talk about is in a second paper by Poisson, where he relates this to questions about vector bundles on elliptic curves, and in particular about something which might be of interest to some people here, abelian vortices. So this goes back a long way. So the situation is you have a Riemann surface C, or algebraic curve C, you have a holomorphic vector bundle on it, and you have a Higgs field, which is not in the adjoint representation, it's in the vector representation. And in order to define stability, you have a real number Tor. And then you say that the pair is stable if for each subbundle this slope is less than Tor, and if phi lies in the subbundle, the slope of the quotient is greater than Tor. So this may, and then if it is stable, then there's an existence theorem for a special Hermitian metric which satisfies these vortex equations. Now, some of you in the audience may well know about this. In particular, I'd like to point out that Oscar, it's now 20 years since your thesis, and it's 34 years since Witten kind of wrote about these in a different context. And Steve, I'm not sure what when your thesis was, but I think you just told me it was 89, 90, something like that. So, so actually these, we know a lot about these geometry of these vortex equations. Witten's observation for the hyperbolic plane anyway is that they were the same as SO3 invariant instantons, but in this more general situation, and the point of view that Oscar had in his thesis, these are the same as SO3 invariant instantons on the curve times P1. So in this case, so what we can do is we can take C to be an elliptic curve, and then V is going to be a vector bundle of rank R plus 1. So there's going to be another R appearing. I mean, there's another vector bundle appearing here. And we're going to take the coprime case of D and R. So it's not coprime for V, it's coprime for the rank of V minus 1. And then you take this parameter, this stability parameter, to be D over R. So this is what Polishchuk does. And then the stability condition says that phi should be a non-vanishing section. And this means, and also that the quotient bundle should be stable. So you're looking at vector bundles which are extensions of the trivial bundle by a stable bundle. So this is a stable bundle on an elliptic curve, and what we know from Atiyah's classification is that up to tensing with a line bundle, there's a unique stable bundle of rank R and degree D if these two numbers are coprime. And he constructed these by successive extensions, but there's Oder pointed out that actually you can get these by taking a line bundle of degree D on the elliptic curve and taking its direct image under an isogeny, under an R-fold covering. So this is the way in which one gets the possible quotients. And then, so we're classifying extensions. So this moduli space of vortices is a space of extensions like this. And okay, by Serre duality, we have this. Now, if you think of Oda's description of W as the direct image sheaf of line bundle L, then that tells you that the holomorphic sections of W are isomorphic to the holomorphic sections of L under this direct image map. L was a degree D, so this is a D-dimensional space. And so actually the moduli space is a projective space which is isomorphic to the dual of this projective space here, because it's parameterizing the extensions. On the other hand, the elliptic curve E itself sits inside this space in a natural way, given by, if you like, the kernel of the evaluation map. You take a point on X, you evaluate a section at the point X, and that gives you a linear map, which gives me a point in this moduli space. So we have a moduli space here, which is just projective space. Now, more importantly, there's a Poisson structure on this. So you've got to describe the tangent bundle to this moduli space and the cotangent bundle. So the way you do this is that you look at this, the endomorphisms of the vector bundle V, the one of rank R plus 1, And end O means the ones that preserve this distinguished subbundle, this trivial subbundle. You have an exact sequence of bundles like this. And then the tangent space, well, this is the tangent space, not to the vortex moduli space, but the tangent space to the moduli of pairs of vector bundle and degree 0 line bundle sitting inside it. So ours are rather more special because we want a trivial subbundle sitting inside it. Anyway, the cotangent space is the dual of that, and well, it's the SED. This is SED duality is giving us this, and then there's some exact sequences here. Let me just put it this way. So actually, so this is the Poisson structure. So you have these exact sequences like this. You have this connecting homomorphism, and then you have this inclusion here. So the composition of these two is a map from T star to T, which is in fact a Poisson structure. It's not immediately obvious that it satisfies the integrability condition, but in fact it does. So this is a way of producing a Poisson structure on projective space, and in fact you can do this more generally with some Grassmannians by looking at different types of bundles. Now, one of the good things about this is that it enables you to study the degeneracy of sigma quite concretely. Because, so the kernel of sigma, so I say the place where the rank of sigma drops, this gives us these Poisson subvarieties. And there's an exact sequence here which tells you how that goes. So, so let's look, I mean, what's the generic situation? The generic situation is where W itself is stable. So wait a minute, which is W, which is, no, okay, so, no, sorry. So W has to be stable, that was the quotient. So in that case, there's just a one-dimensional space of endomorphisms, and so we get this two-dimensional space inside the cotangent bundle, which is in the kernel of sigma. So that's in the case. On the other hand, this particular Poisson structure was defined not on the space of vortices, but we were allowed to change the line bundle inside, and we're also allowed to change the top exterior power of the bundle W. And so there are these two degrees of freedom. So if you like, there's a map from the moduli space to this product of elliptic curves, and this, if you like, is the annihilator of this. So if we fix the line bundle to be trivial and we fix the determinant bundle of W, then actually what we get is something which is well, that's what defines these O plus O. So if you like, there's an induced Poisson structure on this moduli space of vortices with fixed determinant. And okay, so what the important thing in Polishchuk's paper is he shows that essentially this Poisson structure, he reinterprets the result of Fagin and Radisky, saying that this Poisson structure defines a known Poisson structure on on the vector space rather than on the projective space. So let me just flash up what the known Poisson structure is in the case n equals 5. So these are some Poisson brackets of linear functions in 5 dimensions. This induces a Poisson structure on P4. Now, in a way, I got interested in this earlier, last year, and I tried to find out what the structure of this Poisson structure, what the stratification of this Poisson structure was by using these formulas. And it's very difficult to do it that way, and fortunately this more geometric way of Polishchuk actually explains it much better. In fact, let me just show you what happens now in the 3-dimensional case. So we just moved up 1 dimension now from P2 to P3. So this means that we have a line bundle of degree 4, and we're going to take R equals 1. So the R equals 1 is the This was the R, this Q51 here, so that's the 1 in that. So in this case, we're just looking at rank 2 vector bundles on an elliptic curve, which are expressed as an extension of the trivial bundle by this line bundle of degree 4. Well, this particular line bundle of degree 4. And in this sense, if you like, it's just the extension, the map here, the extension class, which gives us the point in the projective space. Now, in this case, D and R are not co-prime, so there isn't a stable bundle, V. So our vector bundle V, our rank 2 vector bundle, is a sum of line bundles. And so you can look at the various degrees of the line bundle U in this direct sum. So now, because the trivial bundle is contained in here, that imposes restrictions on the degree of U, and because you can interchange the roles of the two factors, then you might as well assume that the degree of U lies between 0 and 2. And in fact, the degree 0 case is out, because actually in this case the bundle U is trivial, and then we get a trivial extension which is not in fact stable. So there are just two possibilities here of, well, it seems as if there are two possibilities, namely of the degree of U being equal to 1 or 2. So let's just have a look. On the other hand, it turns out there are three possibilities. So if I take the degree of U to be 2, then what I'm interested in is looking at this formula, if you like, looking at the dimension of the kernel of sigma according to that extension. So in this case, the endomorphisms of V, okay, so the off-diagonal ones are sections of this line bundle of degree 0, U squared L inverse. So there are two possibilities. So in this case, if U squared is not isomorphic to L, then the off-diagonal terms vanish. Therefore, the formula for the dimension of the kernel of sigma is 2 minus 1. It's just the scalars here, which preserve the trivial subbundle. So that's 1. And here we're in 3 dimensions. We're on P3. What's the generic situation for a Poisson structure in 3 dimensions? It's that the dimension of the kernel is, well, the rank of this should be 2. It can't be maximal. It can't be degree. It can't be rank 3. So this is the generic situation then, where this line bundle is degree 2, and we have this condition. So now if we look at the case where U squared is isomorphic to L, then of course V is U plus U, and we have a much bigger space of endomorphisms. In fact, this is just U tensored with the trivial bundle, so we have a 4-dimensional space of endomorphisms. And the ones that fix V is again just the scalars. So we get a 3-dimensional kernel, which is, of course, that's where sigma vanishes. This is only a 3-dimensional manifold. So sigma is vanishing at the 4 points corresponding to these line bundles, these square roots, if you like, of the line bundle L. So you might say that, you might say, well, that's very natural that we have this Poisson structure, and it's a section of a rank 3 bundle on a 3-dimensional manifold. We expect it to vanish at a finite set of points. Here are 4 points. But actually that's not the full story, because if you look at the case of degree of U being equal to 1, and you go through this, what you find that in this case the dimension of the kernel is equal to 3 again, so the Poisson structure vanishes again. And it in fact vanishes on that, what this is intended to show is that it vanishes on the elliptic curve. So actually, the stratification here is that you have generic type, and then the Poisson structure vanishes on the elliptic curve itself, on a curve, but also at 4 separate points. So this is something which we can read off from this vortex moduli space description of this Poisson structure. And this is a 3-dimensional case, which is kind of special, because in this case you can, a section of second exterior pair of the tangent bundle can also be thought of as a twisted one form. And then so the sigma becomes a one form with values in the anticanonical bundle. And then the integrability condition is basically that theta wedge d theta equals 0. It's the Frobenius integrability condition for a foliation. And so the picture is that we have a, if you like, we have a singular holomorphic foliation. And what I've just described to you actually is this picture here. That if we adopt this point of view, then suppose we take two quadrics, if we take two sections of O2 on P3, then if I look at this Vronskin, if you like, S1 ds2 minus S2 ds1, that's a one form with values in O4. O4 is the anticanonical bundle. So this theta is basically describing this Poisson structure. And so what we have is a pencil of quadrics, which they all intersect in this elliptic curve. And those 4 points are actually the 4 vertices of the singular quadrics in this pencil. So this is I mean, we can, in this case, in the case of P3, we can very simply describe it in terms of an elliptic curve of degree 4 in P3 expressed in terms of the intersection of two quadrics. But the higher dimensional versions are much more complicated. So this is the sort of picture that we have. Each of these quadrics is a Poisson surface. So I should say that these are what are called the symplectic leaves, but they fail to be symplectic along this intersection, which is an elliptic curve. So they are themselves Poisson surfaces. And so you might ask, well, how can we find Poisson modules on this? And there's an obvious way in which you might try, but I haven't fully explored that, because what we know is that what we need is a Poisson module on each of these surfaces here, these quadrics. So you could say, let's take a set of points along the intersection and try and do the Serre construction on each of these quadrics. Or better said, suppose we blow up the elliptic curve, and then those points give us some rational curves inside the blow-up, try and do a Serre construction up there. I don't know whether it works, but I mean, that's at least a possible approach. So as you can see, it's pretty difficult in any case to produce Poisson structures on projective spaces. This vortex moduli space approach at least tells you that if you take an elliptic curve embedded in Pn, what's it called, an elliptic normal curve embedded in Pn, then there's a natural Poisson structure associated with that. It's an open question about how many Poisson modules we can find this way. I must admit, almost a year ago, I had the idea that the Horrocks-Mumford bundle on P4 was going to be an example, but that didn't work out. But so it's far better, in fact, to start at P3 and just see what the picture is there. All right, so now finally, let's. What can we say about one dimension? You might say, well, this is stupid because how many Poisson tensors are there in one dimension? I mean, second exterior pair of the tangent bundle is 0. All the Poisson structures are 0. But that doesn't mean that you can't ask for Poisson modules. And in fact, you know, you could say that, I said that whenever we have a Poisson variety, something defined by a Poisson ideal of functions, then there's an induced Poisson module structure on that from an ambient one. So in particular, in all of these cases, on that elliptic curve, there is in fact an induced Poisson module. So what do they look like? So, well, first of all, my differential operator D is now a zero-order operator because the symbol was the sigma. So this is true not just on the curve, but this is true in higher dimensions. You could still ask the question, what is a Poisson module for the trivial Poisson structure? So what it is it's just a section of the endomorphism bundle of V tensored with the tangent bundle. And just in the same way, you can define an action of a function on a local section of V by taking this, so I've written it in the form of a Higgs field, but it's if I evaluate this on the derivative of f, and that gives me my action, And now I want my Poisson action, so I want f and g to commute, and that's equivalent to saying that this phi wedge phi is equal to 0 in this space here. So this is, in fact, I mean, if I'd actually replace the tangent bundle by the cotangent bundle, this is Simpson's definition of a Higgs bundle in higher dimensions. And so it seems reasonable to call this a co-Higgs bundle, just replacing T star by T. So this then is what a Poisson module structure is for the trivial Poisson module. It's trivial Poisson structure. It's not just a holomorphic vector bundle, but it's a holomorphic vector bundle together with a Higgs field phi, but with values in the tangent bundle rather than the cotangent bundle. Well, in one dimension, this condition, of course, is trivial. And so maybe I should just finish up by talking about Poisson modules on P1. So I should say that I have a student, Stephen Ryan, who's writing his thesis about these co-Higgs bundles in general on P2 and other things, but in particular on P1. So you might say, what is there really to find out about Poisson modules on P1? Well, some things are very familiar. So what is it we've got? We've got a vector bundle V, holomorphic vector bundle on P1. We've got a section of the endomorphism bundle twisted with the tangent bundle, so that's O2. We have the notion of stability, of course, slope of fine variant subbundles. And so in the co-prime case, what we're going to have is a smooth moduli space. This dimension, or you might say, let's take the trace to be 0. And it's like going from GLN to SLN. And then we get something of dimension 2n squared minus 2. What else can you do? You can do the usual spectral curve construction. You can take the characteristic polynomial of phi. This gives us some sections of O2, O4, O2n, etc. You have this moduli space, and you have a proper map from the moduli space onto the direct sum of this space of sections. And the generic fiber is, in fact, the Jacobian of this spectral curve. You get the vector bundle on the Higgs field by taking the direct image sheaf of a line bundle on the spectral curve. So this is all very familiar in the case of Higgs bundles. The only difference is in the Higgs bundles, this is an integrable system because the moduli space has a symplectic structure. In this case, we don't have it. I mean, the dimension of the fiber here is n minus 1 squared, and the dimension of the base is much bigger than that. But still, you might say, okay, this moduli space has an expression as a fibration by abelian varieties which degenerate at certain places. And you can describe these equations by a moment map. In this case, you have to choose a metric on P1 in order to describe the stability condition in gauge theoretic terms. And once you've solved that equation, you have this Morse function, the global L2 squared of the norm of the Higgs field. And so one of the things you might do is to try and find the Poincare polynomial of this moduli space by looking at its critical points. And but it's here that you get a rather interesting situation. So this question, what is the minimum of the norm squared of the Higgs field? So in ordinary Higgs bundles, it's an absolutely trivial question because the absolute minimum is where the Higgs field vanishes and the bundle is stable. So inside this big moduli space of vector bundles together with Higgs fields, we have this copy of the moduli space of stable bundles. But here on P1, there aren't any stable bundles. I mean, every bundle is a direct sum of line bundles. So you can still ask this question, but the point is that that phi actually is never 0 on this moduli space of stable bundles. So what happens at the minimum? What is the minimum? So this is something which Steve has been looking at the past couple of weeks, so let me just point out what he's found out. Well, first of all, you can ask, well, what about the holomorphic structure at a minimum? Well, it's not hard to see that actually, so here the simplest case is taking the degree to be -1 in order to get this co-prime situation. And then it's perhaps not surprising that at a minimum the holomorphic structure is the generic holomorphic structure for a vector bundle of rank n and degree -1. It's just the direct sum of n-1 copies of the trivial bundle plus O-1. But then what happens? So at each critical point, what we know is that the Higgs field becomes a chain. So you can express these critical points as the fixed points of a circle action, and then you express as many people in the audience know here, these critical points in terms of a Higgs field, which is expressed as it's a nilpotent Higgs field, which is part of a chain like this. So then you can ask, well, what about the structure of this chain? What structure do these individual vector bundles have at this absolute minimum? And the answer is rather strange, that if the rank n is, so basically you write it as the form 3 to the k plus m, where m is between 0 and twice 3 to the k. And then, so the last one, the one at the right end, is the O-1. All the others are trivial, but the ranks go up like this. So it's 2 times 3, 2 times 3 to the I-1, all the way to the end, which is, I haven't mentioned it, but the last one is m-dimensional. So, and then what do you get? Then what you find is that the dimension of this critical submanifold, unlike the ordinary Higgs bundle picture, it's not a fixed dimension. It's not the same as the dimension of the fiber, of the generic fiber. It has this dimension. So sometimes it's 0. So when m is 0, it's 0, then it goes up again, and then it goes down again to when m equals 2 times 3 to the k, where it's 0 again. But when m is 2 times 3 to the k, n is 3 to the k plus 1, and then you need to put on an extra factor. And then what you find is that actually this critical submanifold is the Grassmannian of n-planes in this space. So here then is a curious picture. I mean, which is, initially you stand back and you say, well, this is very like Higgs bundle theory, and then you say, well, actually there's more to it than that. And so I should say that this is one of the things that Steve is doing at the moment, is trying to find some inductive formula for the Poincare polynomials for this, and we have some conjectural formulas from postdoc Sergei Moscovoy, which so far seem to fit these things here. So all I'm trying to say here is that actually, even if you get down to the most trivial situation of the projective line, and you ask for Poisson modules on the projective line, then nevertheless the moduli space throws up some new features, features which need some new attitudes in order to resolve them. Well, I better stop there.